Right, we have discussed conversion of sand to polycrystalline, then polycrystalline to monocrystalline. And now we know how do we actually do the growing process. Okay, so before we move on to the details of wafer preparation, so let us recap a few things on the previous topic. Okay, so Czochralski and float zone process, what is the difference between those two processes? So what can you highlight differences between float zone and Czochralski process? Let's just lump the questions together as one. What are the main differences between the two processes? Fatima Zahra? Fatima Zahra, can you hear me? Okay, right. Right. So what are the differences between the two processes? Maybe you can say one. You can unmute yourself. Okay. Okay. Float zone uses RF coil. And how about Czochralski process? What does it use? Apa konsep atau apa mekanisme yang digunakan oleh Czochralski process to do the growing? Anyone else could help? Fazira, what's the difference between Czochralski and float zone? Seed crystal, yes, yes, seed crystal, but both use seed crystal. Apa beza RF coil punya mechanism and RF coil pula, FZ and CZ punya mechanism to grow monocrystalline silicon? Fazira? Fazira, can you hear me? Oxygen concentration, okay, what would you like to say? Oxygen concentration, what's the difference between those two? So what's the difference in terms of oxygen concentration? CZ is higher than FZ, okay. Why is CZ higher than FZ? Kenapa CZ ada higher concentration of oxygen than FZ? Naim? All right, Shami, CZ uses crucible, so therefore, so if you use crucible, then what makes the oxygen higher? Ada satu keyword saya cakap semalam during the class. Apa beza yang menyebabkan the oxygen and in fact carbon is higher in CZ compared to FZ? So the keyword is contact, okay, contactless and contact punya process, right? CZ is contact. CZ involves contact process antara crucible and the bath, the molten bath, molten silicon. And float zone, on the other hand, uses non-contact RF coil to do the melting, right? To do the melting. So the key there is melting process. So melting in CZ is carried out by uh, to melt the silicon into molten silicon, and on the other hand, float zone uses RF coil to do the melting, the zone melting crystallization process. So due to the non-contact nature of the float zone, so you also minimize the concentration of the oxygen and carbon. Okay. So what is dopant segregation coefficient? What is dopant segregation coefficient? What's the meaning of K naught? Apa maksud K naught ni? Liana, what's the K naught? Apa dopant segregation coefficient tu? Purity? Is it? This one is previous question, right, Fazira? So what is dopant segregation coefficient? Ratio, okay, ratio of how much dopant will be in the ingot, bukan sample, sample general, will be the ingot in comparison to dopant incorporated in the melt, okay? So CS over CL, kan? CS over CL. So, right, why K naught is important during silicon growth? Give examples. Kenapa dopant segregation coefficient tu important? Why is it important in the growth process? Consistent ingot. Okay, what is consistent? What do you want to be consistent in the ingot? In relation to K naught. What do you want to be consistent? Yes, you want it to be consistent, but what is the parameter that you want to be consistent? Purity? Yes, you want to have high purity, good purity, but then it's not in relation to K naught. Hazika, homogeneous doping. Yes, exactly. Homogeneous doping. So you want to have, if you grow 1 to 2 meters of longer, actually just to scale down, 1 to 2 meters of ingot, you want the doping level to be uniform, to be homogeneous across the 1 to 2 meters, and in fact across the diameter as well. So then only when you slice the ingot into hundreds of wafers, you will have wafers with uniform resistivity or doping level across the whole ingot. Okay. All right, done. So let's move on to wafer preparation for this class. So wafer preparation is about converting silicon ingot into silicon wafers. So you can see the image there. So what we're going to do next is, now we've got the ingot ready. So whatever the length is, whatever the diameter is, we want to cut the ready ingot into silicon wafers, right? And that can be done by a couple of methods. And there are there are several concerns around the wafer preparation that you have to understand before we actually do the fabrication processes on the wafer. All right, it starts off with silicon crystal growth, which is done by chochrality or float zone process. Then the moment the silicon ingot is ready, so we now have to remove the seed and the tail, which reflects the edges of the ingot. So dekat depan dan kat belakang, or if like dekat atas dan kat bawah, right? Remove the seed where you actually induce formation of the crystal according to what you want, either 101, 100, or not. And the tail, remember last time we've discussed that the tail, yesterday I think we did discuss about the float zone process. where it accumulates impurities when it does the melting process until the top end of the ingot, right? So that's why you have to remove um, the edges of the silicon ingot. Okay, then we now have to, at the moment you have removed the seat and the tail, we have to grind the bowl into cylinder. So I did mention yesterday that after we finish the growing, the edge of the wafer will not be perfectly round. So then we have to grind. We have to grind the whole ingot or the bowl, if you like. Either one is fine, into a perfect cylinder. So whether it's 2-inch or 4-inch or 6-inch or 8-inch or 10-inch or 12-inch or 18-inch. So if you talk about typical wafer fab operation, so they normally use 8-inch. The latest fabs use 12-inch and some even go up to 18-inch. If you talk about low-end wafer fab, some use 6-inch, and if you talk about lab, usually we either use 2-inch or 4-inch. Okay, so the diameter of the ingot will be varied according to the customer requirements. So the plant which does the growing process so must actually have difficult we call different, not difficult, different sizes of the ingot growth capabilities. So the moment we've grind the bowl into perfect cylinder, we then determine the orientation base, which is based on the seed that we use during the growth process. So it's either 100 or 11 or 101 or whatever. Then we have to grind the flats. The flat here means bila kita dah ada satu perfect cylinder, we then have to remove certain what we call certain area of the circumference as a flat area to determine to label the orientation of the ingot so that we know what sort of wafers are we working on, right? Then we need to the moment you have done the grinding of the flats, we need to flatten certain area. We'll see later on in the next few pages. We then will cut the ingot into wafers, so it depends on what sort of thickness do we want for our customers. So for fab or slab or whatever, then we have to edge, remove the round the at the edge area, right? Then the wafers will go through lapping process so that we can refine the thickness to the correct thickness. So the thickness will actually vary. Let me show you one package, right? Dekat tangan saya ni ada satu wafer pack. I don't know, you probably cannot see the details. But this is a 2-inch. Dalam ni ada wafer, you can see from the back. Nampak kan? Nampak tak dari belakang? Nampak wafer yang dah di slice kan? Dah duduk dalam kaset lah basically. This is a cassette ordered for no lab. So this is a 2-inch punya wafer cassette. So dalam ni ada 25 wafers. So you can see some labels on the front side. So it's Semiconductor Wafer Incorporated. So you can see the label there. If you can see, I think you can. So wafer resistivity, wafer type, orientation, what else? This one is 2-inch of 50 mm of 5 cm, 1/3 of baris pendek, boron as the dopant. Okay. Diameter is 2-inch, so thickness is 275 micron plus minus 25 micron as the tolerance, and then 1 to 10 ohm cm, 1 to 10 ohm cm resistivity, and then single side polish. So bila kita potong wafer ni like this into this, the front surface and the rear surface can either be polished or both surfaces can be polished. How much does it cost? Okay, good question. Okay, cuba teka berapa harga satu pack ni? If you talk about 2 inch, 1 to 10 ohm cm, 275 micron, 25 pieces dalam satu pack ni. So you try to guess here di chat box berapa harga agak-agak. 25 keping satu pack berapa harga? Come on, let's start now. Just put any figure you think is possible. 25 pieces. 500. Okay, put in RM 400, 500, Fazira 500, Faika 400. Lagi. Let's take another three guesses. Satu pack ni. Then you will appreciate the value of each wafer. Sekarang kita cakap one pack. How much is one pack? Faika said 400, Fazira 500. Okay, the rest? Jenny, how much? What's your guess? 1,000. Shami 1,000. Hazika 3,000. All right. Okay, next. Ada lagi? After Hazika 3,000. 1,400. 500. Ada lagi? Last one. 5,000. Oh, another guess. 5,000. 1,000 to 5,000. Okay. So the right answer goes to Hazika. Right. Good one. It's 3,125 for this 25 pieces 2 inch. 3,000 So this particular pack cost me 3,125. So kita bahagi kita tengok berapa harga per piece. 3,125 divided by 25. So it's 125 RM 125 per piece. So kalau you buat FYP hari tu kan, you apa ni student saya Syamim, Liana pakai silicon wafer kan. Izian pun, Fazira pun. So each 2 inch wafer cost me RM125. So kalau you potong 4, then that's 30 ringgit per 1 quarter. Okay. So bila you tahu harga ni, you will appreciate more the value of each wafer. So each wafer, kalau you misprocess, so you will hear this more often if you go into wafer fab. Misprocess. Kalau you misprocess satu wafer yang 2 inch, you do wrong process lah basically, or you forgot one step, or you got different or wrong parameters for a certain process. So you actually doing a misprocess, and that particular wafer is gone. So 125 ringgit is gone just by pressing a wrong button, for example. Okay. So yeah, 25 pieces, 2 inch. So in this case, the wafers are all here lapped to 275 micron plus minus 25 micron. Okay. So masih lapping tu dia, kita akan tengok nanti lapping, what is the lapping like. So it's lapped to 275 micron plus minus, then they are categorized together for sale. Then they are chemical and mechanically polished as well to make sure that the surface of the wafer is flat and smooth and conform to the specifications. We'll see the specs. And finally, followed by chemical cleanup before they are packed and then sold to the customers. Okay, so this is all the processes that need to be gone through by each silicon wafer before they are packed for sale. Okay, ingot sizes. Most ingot for IC manufacturing today is 200 mm or 8 inch. Silterra is doing 8 inch. I think Infineon is doing 8 inch as well. We don't have any bigger wafer size in Malaysia wafer fab. So if you go for GF or Intel, Samsung, they might be working on 12 inch. Some in fact have 18 inch as well. So wafer fabs in Malaysia, Silterra, Infineon, Fuji Electric. We also have Mimos. We also have On Semiconductor in Seremban, Mimos in KL, Fuji, Infineon, Osram, Silterra, Kulim High-Tech. Okay, so latest technology adopts 300 mm or 12 inch and also 450 mm for 18 inch. Ingots are characterized by orientations of the crystal, so you will normally use for wafer fabs 1, 0. So some applications might need 1, 1 as well. So before the ingot is cut into wafers, 1 or 2 flats are grounded. You'll see later on. Kita akan macam label dia, kita akan tanda dia. Or we basically can also say that we mark the ingot before we cut them into wafers. Okay, they look like this, wafer flat, tapi tak semua, well, normally each wafer either adopt one of this. So each wafer is given either a notch or a flat edge. So 111 typically looks like the leftmost, right? You grind there. And then 100 P-type is given two flats, if you like, two flats on the left and at the bottom. So to mark it's P-type 11 or P-type 100. So N-type 111, on the other hand, is given a diagonal 45 degrees and a bottom flat as well. And if you talk about N-type 100, it's given two flats on the top and at the bottom part. But normally, if you talk about wafer fab, we normally work on 100, like the one at the back there. Here. Yeah, see it. Color, yeah. Okay. Normally for fab we work like this. We use this one. We have a notch here. Ni yang lubang kecil ni kita panggil notch. So you normally have a perfectly round wafer. It's not flat for my drawing here. And you have like that. Got a notch. Selalu kita pakai notch ni dalam wafer fab. We hardly have the flats for wafer fab. Okay, kenapa kita perlu ada notch? When you learn later on all the processes in the fabrication, certain processes are sensitive to alignment. Maksudnya bila you nak buat proses tu, katalah ni notch kat bawah ni, assuming this is the notch, I don't have any wafer with a notch. Katalah you ada notch kat bawah ni, something like that. Then certain processes need the wafers to be aligned like this. It cannot go like that. It cannot go like that. It cannot be diagonal. It cannot be random. It has to be like this, perfectly like this. For example, lithography process, some other processes as well. The moment you have the knob, then what it does in the fab later on, it will do home alignment. They call it home alignment. So or some call it zero alignment. So kadang-kadang wafer yang masuk by the robot arm tu is random in nature. It may sit at any angle on the robot arm. Then bila robot arm hantar masuk like is it put down there, and then before the process actually starts, the wafer has to be aligned to home position or zero alignment. So dekat situ kita akan ada sensor, kita akan ada detector kat bawah, then you have a notch that will open a way for the sensor to work. Kalau you tak ada notch kat itu, then it's going to block the what we call sensor process. So dia akan align sampai dia jumpa detector to detect the position, then it will call zero alignment or home position. Then only the process can start. Kalau dia tak jumpa home position, the process will not start. Okay, so that's one way to control process in wafer fab. So that's why the notch is important. Okay, lattice orientation refers to orientation of silicon crystals. It's either 1, 0, or 1. Orientation is based on seed crystal. So kita dah tengok FZ and CZ punya seed punya proses kan. If you put in 1, 0, 0, then you're going to get 1, 0 for the ingot. If you put 1, 1, you're going to get 1, 1 for the ingot as well. So you can actually decide by the type of seed that you use for the growing process. So quick question, what type of silicon wafer orientation used in IC fabrication and why is it so? If you're talking about transistor fabrication, katalah kita nak fabricate CMOS, then what sort of orientation we use in the wafer fab? So let's give your guess. Agak-agak orientation apa kita pakai process for the fabrication process? Anyone? Put your guess there in the chat box. Or you want to talk. Anyone? Guess the orientation now. Aniza. Aniza, you around? Come on, let's guess. 100, right? Aniza guess 100. Any reason for your 100? Why do you think 100. Anyone else? Anissa said 100. How about Amira? Amira, what's your guess? 111. Any reason for your 111? Kita nak fabricate transistor kan? CMOS. Right, so let me... I'll give you 10 seconds. Any other guess while I'm searching on this? Anyone else? Okay, ada lagi? Yishin, what's your guess? We need to fabricate transistor now. Do we use 100 or 111 or some other orientations? Assuming you're running a CMOS fab. Anything, Yishin? One, 1, 0. So we now have a variation of answers. Okay, when we fabricate a transistor, what are we after? Kita nak apa dari transistor? What's the main output that you want from the transistor? Kalau kita move from teknologi node yang besar kepada teknologi node yang kecil, what is our main goal? If you go back to Mohd's law, what do you want to get from the new chips? Kenapa kita buat yang sophisticated? What are we after? Small size, okay. What else? So bila you beli produk, are you after? Bila you beli produk, you tanya tak kat kedai tu, transistor ni size berapa? Ada tanya tak? What are you after as a customer? Tak tanya. Etching? Okay. Jawapannya senang. Kalau you pergi kedai, you tanya kat kedai tu, you tanya apa dekat produk tu. Assuming you beli laptop lah, beli laptop. But laptop kan driven by transistor, dia punya switching process. Speed, right? Speed. Okay. So if you talk about speed, yes, the answer is speed. Then you're talking about 2.8 gigahertz or whatever. You tengok 1 gigahertz, 1 gigahertz, alamak, too slow. Then you might want to go for 3 gigahertz kalau dah ada. So then speed. So if you go back to physics of semiconductor device, what determines the speed of a transistor? Parameter apa yang determine the speed of transistor? If you recall 386 last semester, what actually determines the speed of the transistor at material level? Maksudnya silicon lah, sebab kita pakai silicon kan as our CMOS. What determines the speed? You still remember mu? Doping level, yes, in the rack. Do you still remember mu? What is mu? 386 last semester. What is mu? I cannot type it here because it's mu. Ingat lagi ke mu? Sudah lupa ke mu? Sudah lupa. Mobility, remember mobility? Hold on. Mm, okay, can you see the whiteboard now? Okay, good. You still remember this? Hold on. Why is it not working, my whiteboard? Hold on. The problem is get my whiteboard. Okay, you can see the whiteboard, right? Sorry, I think we have a problem now. Can you guys hear me now? Saya ada problem sikit tadi. Boleh dengar saya tak? And can you guys hear me? Okay, still okay. Hold on. Ada problem tadi. Let me try on this. Okay. Let me reshare. Okay, all right. Okay. Okay, it's determined by mu. So it's determined by the mobility of the carriers in the material. So if you talk about silicon, then it's silicon mobility for either n-type or p-type. So if you compare, nanti you can revisit back. You can revisit. If you compare the mobility for 100 and 111, yang mana lagi tinggi? Mobility of electron, for example. If you talk about 100 versus 111 for silicon, then yang mana lagi tinggi mobility? We learned last time in 386. 100 or 111 or some other orientations? Shazwani, 100 or 111 or some other orientation with the highest mobility? Anyone else? Yang mana lagi tinggi orientation? Apa mobility? Tamim? No answer. Okay, you go find out. They try check. Go home and find out. Okay, so you can see the slide, right? Can you please confirm? Can you see the slides now? Okay, all right. So 100 versus 111. The latest orientation is used for CMOS. Usually is 100 untuk fast punya operation. Okay, 100 due to mobility of carriers for 100 compared to 111 or some other orientation. Right, 111 is used for some other application where speed is the main concern. This is the very same thing orientation that we've discussed is now the flat. Okay, so wafer preparation steps sama macam tadi yang saya sebut tadi. So growth, shape, slice, lapping, etching, chemical polishing, and then we do the cleaning. inspection, and then followed by packaging. Then the wafers are packaged and then ready for sale. So let's go to the slicing process or sewing process, if you like. Usually it's done by diamond saw or diamond wire saw. So this is how it looks like. So the example that I take here is from square silicon bricks. So the silicon brick is used for solar cell fabrication. Sebab solar cell kita tak nak pakai apa ni round, kita nak pakai square. Any idea for that? Kenapa untuk solar cell kita nak pakai square shape silicon instead of round shape silicon? Anyone has ideas for that? Kenapa kita nak pakai square shape instead of round shape? Zuriati, any idea for that? Why do we want to use square shape? This one is square shape. Usually it's used for solar cell. Tapi dia silicon juga. For silicon solar cell. Right. Any ideas Zuriati? Kenapa kita pakai square? Or anyone else? Untuk solar cell. Yes, higher surface area, good. Right, kita nak, if you look at solar panel, kita nak semua area ada solar cell lah kan. Kita tak nak lah pakai bulat. If you pakai round shape, then you put the next round shape, ada, you'll see the opening, right? You'll see open areas a lot. So kalau you pakai square shape, you can close the whole surface with solar cell, then you can harvest more current or higher current. Okay, that's why dalam solar cell kita nak pakai square shape. Okay, higher surface area. So with wire saw technique, wire saw ni kita pakai wire, dia ada slurry kat situ. Slurry tu macam grit, biji-biji kecil. You wanna use a very thin wire to cut. Okay, when you do the cutting process, you want to use a wire that's very thin. Sebab kalau you pakai wire yang thick, then bila you potong, katalah you ada ingot yang bulat, then you pakai wire yang besar, then if you cut the areas between wafers, you will have a lot of silicon loss. Sebab you pernah tengok tak orang pernah potong kayu kan? Pernah potong kayu, ataupun kalau you go to kedai perabot, kalau tengok you pakai gergaji yang mata besar, bila you potong kayu tu, dia akan produce dust, debu kan. So dust tu is actually a huge loss for silicon wafers. Kalau you imagine it's the very same wood as silicon ingot. So it's called curve loss. Down here, it's called curve loss. So that means you cut the area, so you're going to lose so much dust. So that's called curve loss. So that's why when we do the cutting, you want to use a very thin wire so that you can do the cutting process efficiently, and then you generate less dust. So therefore less curve loss. So you don't want to use, if you look at this note, it creates 10 to 20 micron damage on either side of the wafer, and then you're going to have curve loss like hundreds of micron as well. So in between usable wafers, okay? So you want to minimize that. So wire sawing, this is how it looks like. If you have a silicon ingot, so it's either silicon square brick ataupun round brick. So you're going to use this sort of configuration to do the cutting process. So it's quite a dirty process because it involves slurry to do the cutting. You can watch this video later on. So dia akan move along. They can move along the ingot to cut. Across, sorry, not long, across the ingot to cut. So wire sawing, this is also the representation of wire sawing process. So you can see there, area yang ni, this is the wafer punya area nantilah. So this is another wafer. So this is another wafer. So katalah you wanna cut 250 micron wafer thickness. So this is another wafer. So your whole thing here will be the ingot. So area you akan loss is this area. So it's defined by the diameter of the wire. Okay, this one will be lost. Dia akan hilang. So maksudnya kita dah grow panjang-panjang tu. So quite a significant portion of the ingot will be lost to the cutting process. So that's why innovation in the cutting process is equally important as well, even though it looks quite straightforward. Tapi minimizing curve loss to is of a high priority, okay, in this cutting process. So plated saws can also be used, diamond tip plated saws. So this yang biji-biji that you can see here ni is actually abrasive slurry. Slurry ini will actually help the cutting process and makes it more efficient. Okay, sebab you ada macam biji-biji tu lagi senang potong. It's more efficient. Okay. So wafer manufacturing, silicon crystal is sliced using diamond tip wafer saw. There are many technologies to do the cutting process. So among the prominent ones are diamond tip wire saw or wire saw. It's categorized by thickness. While doing the cutting, we are actually inducing damage on the wafers as well, on the wafer surface. Sebab tadi after you do the cutting, you have the slurry on the wires or on the saw. So you're actually introducing friction to the surface and introducing damage as well on both surfaces, on left and right side. Right? Etch wafers in chemical to remove any remaining crystal damage. So that's called crystal damage when you do the cutting. So therefore, it has to be followed by a chemical cleaning process to do damage removal. Okay, damage removal. Then polishing smooths uneven surface left by sawing process after the etch removal, the damage removal process. Okay, ingot diameter grind. So this how is done. So we start with our ingot after the Czochralski process, if you like. So then we remove the seed and the tail, then you're going to end up with this one, and then you need to grind the fat to mark your orientation. So you have to grind the flat according to the categories that we have seen just now. Either it's diagonal or bottom or top or combination of any. Okay. Okay. This is internal wafer saw process. It can be done as well. So this notch looks like. Usually, if you look into wafer fab, this one on the notch area you will have a scribe ID. It's called scribe ID. Ini akan identify the wafer. So kalau any problem happening to the wafer, then we'll go to the scribe ID to detect where the problem is. So it's like that at the edge of the wafer. So it's not perfectly squared, if you like. So it's not perfectly squared. So it has a bevel there on the edge of the wafer. So saw damage removal. So it's done after the cutting process in order to remove the damage. So you try to identify what chemicals are used for the damage removal. So the goal is to remove the damage before we do the fabrication process. Dimension, I think we just stop here first and then we continue. Tomorrow is what, Wednesday? We'll continue on Thursday. So I want you to look into the saw damage removal chemicals, and then we'll start off with this page on Thursday. Okay. All right. Any questions for today? For today's class, any questions? So small, okay? All good. is there any difference between, is there any difference when only one side polish and both side polish? Yes, there will be a difference. If you, okay, if you if you look at wafers, you can either be dealing with single side polishing or double side polishing. So typically, if you talk about wafer fab, then it's usually double side polishing. So bila double side polishing, you akan nampak dua-dua surface depan dengan belakang tu shiny, right? On the other hand, if you look at a single side polished wafer, so you akan nampak one side shiny, one side is not shiny lah. It's not shiny. Dia macam color grey sikit lah, grey color. So if you look at wafers with those kind of surfaces, maksudnya is either double sided or single side, you will be able to detect the difference, right? So usually either you go for single side polishing or double side polishing. It depends on what sort of application. So for this particular case, for my case, it's one side polish. So that means I use this one for solar cell because I only need one side. I don't need both sides to be polished. Tapi untuk IC fabrication, both sides kena polish, because there will be effect of surface tension or handling or robot arm capability. So it will somehow affect the automation as well, even though there's no processes done on the rear side of the surface. Okay, it's more on the handling, processing, identification, sensing kind of thing, because we hardly process both sides to produce our device. Okay, Shamim, any other questions? So normally, if you look at SSP, single side polish is normally labeled as SSP, single side polish, or kalau kita order wafer yang double side polish, it's labeled as DSP. Right? It's either SSP or DSP. Single side polish, double side polish wafers. Okay, ada soalan lain? Tak ada? All good. Then inshallah we're going to continue Thursday on the debris removal. Then we'll move on to wafer characterization after we've done with the wafer prep. Okay, so see you Thursday, inshallah. Bye bye. Take care. Assalamualaikum.